Good afternoon, everybody. Thanks for the invitation to talk at the seminar. My talk about absence of normal heat conduction in strongly disordered interacting quantum chains. This is based on an archive preprint with Lydia Giacomin, Francois Huveneers, and Oskar Prosniak. Talk is about the following basic question. So assume you have a macroscopic system where the energy density originally is inhomogeneous, and it's inhomogeneous in a macroscopic way. So in the left part of the system, the energy density has some value, and on the right part of the system, the energy density has some other value. Yeah, so there was something in the chat, but I ignored the chat, right? Okay, and now you expect, of course, from thermodynamics that this energy density will flatten out, at least on a macroscopic scale. Of course, microscopically, there will be some fluctuations, but macroscopically, it should flatten out. And we call the time scale on which that happens tau L. Of course, would have to define it more carefully, but I will later make all of this precise in a slightly different way. So normal diffusion would mean that this time scale is proportional to the length of the system squared, which is finite conductivity. There is a phenomenon which you could envisage, which is subdiffusion. If the transport is slower than diffusive, then this time would be L to some higher power. That would basically mean that the conductivity vanishes, right? And then there is another phenomenon which will play a role, and that is if the system would be localized, and I will define what that means, then this time scale would be infinite. You would never reach a macroscopically homogeneous energy density. These questions have been investigated. They have been investigated since, I guess, since 60 or 70 years, but I will assume a very specific context. And in this specific context of strongly disordered interacting quantum chains, I think that the focus on these questions, or at least the broad focus on this question, started by a paper of Altshuler et al. In 2005. And they predicted that in strongly disordered quantum chains, the conductivity would indeed vanish, which in the language of this slide would mean that you would have the tau L would be bounded below by Lp with p bigger than 2. Later, in the years after that, this expectation was sharpened, and people started believing that perhaps tau L is just infinity, which I called localization here, and which is usually then called many-body localization, to stress that this is about interacting systems. Yes, so I should already perhaps here say that I'm interested not in systems close to the ground states, but systems where the overall energy density is finite. So expressed in temperature, we are far away from zero temperature. So this was the state of affairs in around 2010, 2015, and then in the last years, new numerics were done on this problem, starting with the group in Ljubljana, Suntais et al., and one of these was also by Dries Sells, 2022, and a lot of papers in between. And these papers put all these predictions that were made above in doubt, right? So both the prediction that the diffusion constant would vanish here, that there would be no finite conductivity, and certainly the prediction that the system would just be localized, the time scale tau L would be infinite. So this is the questions that I want to talk about. Yes. Now, in principle, you could investigate this problem for classical or quantum mechanics. I will speak about quantum chains. And we also believe that all what we are going to say is specific to the quantum world. So we will have a Hamiltonian, and this is a Hamiltonian of the electron chain. So we have on each side, we have a Hilbert space, which is just a qubit. And then there are Pauli Z operators, Pauli X operators, and Pauli Y operators, which actually are not present in this Hamiltonian. And the dominant term of the Hamiltonian is the first one, where I have a disordered field. So HI is disordered, and the field points in the Z direction. HI are IID random variables, for example, distributed uniformly on the unit interval. Gamma here is the small parameter, and by making it small, we are basically in the high disorder regime. There is here another term, third term, which is an interaction. The only reason that I added this term here is that otherwise everything would be trivial, but actually you can forget about this term for the rest of the talk, because I will try to I will never come back to it anymore. It plays no role in our proof and in our discussion, except that if it would not be there, then the problem would be trivial. Now, what is very important for us is that everything we are discussing should be robust. Okay, so I have here a specific Hamiltonian, but everything that I'm going to say should hold true if you would replace this perturbation gamma xi by something different, as long as that different thing is basically quasi-local, or let's say local even, around side I. So I indicated here by some operator OI, which can be, I don't know, X or Y or Z, and then O at two neighboring sides, which can be whatever you want, but should be smaller, should come with a prefactor gamma squared. Okay, and I stress this very much because if I think back of the previous slide, right, of what kind of behaviors you can get for systems, I think you could engineer more or less any behavior that you want. For example, you can certainly have ballistic transport, you can have superdiffusion, but these things are usually not robust in the way that I want to stress. They are usually not robust if you would add some small perturbations or change here a perturbation into some different kind of perturbation. So this is very important for me, that whatever I will say should be robust. Okay, good. Now, I said that we are speaking about absence of heat conduction, about zero conductivity, about subdiffusion. I did not make any of that very precise. Now I will introduce the setup for our theorem. So you could, it's perhaps a little bit physics-like, but this is the setup of which we thought that it requires least details, least subtlety. Okay, so we have this chain sitting between two baths. There is bath 1 and bath 2, and the total Hamiltonian governing the system is the Hamiltonian of the chain, HL, Hamiltonian for the first bath, Hamiltonian for the second bath, and then some coupling operators V1 and V2, where V1 sits between bath 1 and the chain, and V2 sits between bath 2 and the chain. And then we want to look at the maximal non-equilibrium stationary current that you could chase through this system. So I'm going to define that in a very low-key way. I'm just going to look at the transported heat. And here, so what I have here is the difference in energy in the path number 1 between time t and between time 0. So this time t here, of course, refers to Heisenberg evolution with the entire Hamiltonian. So I look at that in some initial state. Psi is an initial state. It could just as well be a density matrix. It can be anything at all. And I'm going to look at this heat transport. And at the end of the day, I'm going to divide that by the total time, and that is then something as a current. Now, of course, this total heat change, or the energy change in bath 1, is bounded above by the size of bath 1. So it's very important that you allow the baths to become infinite, or to at least become much larger than the system, which is done here by the supremum. Supremum over baths means that you can have any bath space, any bath Hamiltonian that you want. You are all allowed to consider that. You take the supremum, and only then do you divide this energy transport by time. And then you take the limit supremum as time goes to infinity. And that you could call the maximal non-equilibrium stationary current. It's stationary because it's stationary in the sense that it's an ergodic mean, right? You wait a long time and then you divide by the time. Of course, you might prefer to see something with a temperature on the left and a temperature on the right, but that could all be incorporated in that framework. Okay, so this is my quantity of interest, this maximal non-equilibrium stationary current. Good. And then the theorem will say the following, that if this perturbation gamma is sufficiently small and with very large probability, this maximal non-equilibrium current is bounded by the system size to some negative power, and the negative power can become as negative as you want if you take gamma small enough. So in particular, the negative power can be smaller than 1. And if the negative power is smaller than 1, then you see that you already, the resistance of this chain is not 1 over the length, it's smaller than 1 over the length. And that means that you have no normal conductivity. Right, so then we multiply this current by L, and that would, in expectation or large probability, that would then go to 0 as L grows to infinity. So that is what it means for us to have vanishing conductivity. And that is also our theorem. Now, as I said, this setup was chosen to have least assumptions and least details, least assumptions about ergodicity, which we anyhow cannot prove. So we could just as well have gone for a definition via linear response. That would have worked just as well. There was a similar recent result by Christopher Baldwin, where the difference with respect to our result is that they allow the disorders field to have very heavy tails. And then there is another mechanism that basically leads to the same result. So I have up to now almost or not even spoken about Anderson localization. Of course, chains that are Anderson localized allow for a much stronger results. And the reason that I'm not talking about that is that it's not in my framework. I'm interested in robust systems. So in particular, there can be interactions. And so I'm not speaking about non-interacting chains, where you can prove much stronger results. I'm also not speaking about fine-tuned chains, where you can also sometimes prove stronger results, right? That's something that I already said. I'm interested in robust results. Okay.
Wojciech,
now,
there is a question. There is a question
yes.
from chat. So this person missed a part of the talk. Does B2 play a role in your expression?
B2?
Or B1 and the second best? Yeah.
Yeah, you see. So, okay, that's a very good question. So, it's just as a matter of convenience or perhaps even laziness that I chose here the energy change in BOT 1. I could just as well have chosen the energy change in BOT 2. You see, because the difference, everything that BOT 1 wins has to be gained by BOT 2 up to something of order L, right? But L stays finite and you allow the time to go to infinity. So the difference in the transported energy would be something of order L, but when time goes to infinity, this would get divided by T, and so that is irrelevant. Okay,
Yes.
so for the same reason, I could have defined this current in a much more physical way by measuring the heat flow in the middle of the chain. It just doesn't matter because all these things are related up to quantities bounded by L, which vanish then when taking the limit T going to infinity and dividing by T. Okay, good.
Wojciech, may I also ask a quick question on
Yes,
the picture?
yes, sure.
Just about the couplings, you didn't say anything. Do you also take a soup over a certain class of couplings, or?
Yeah, but okay, but now you should also not become too nasty, right? The couplings have to be bounded in norm by 1, and let's say that they should work only on the first 10 spins of the chain. V1 should work only on the first 10 spins of the chain, and V2 can work only on the last 10 spins of the chain. Is that okay?
Yep.
Okay, good. So now I spoke about subdiffusive bounds, and now I will introduce another notion that also plays a role in my talk, which is this many-body localization. So let's give a definition of that, which is not a very realistic definition, as I will point out later, but is precisely what is needed for this talk. So HL, the chain Hamiltonian, being a Hermitian matrix, can always be diagonalized in Z basis, or in any basis, but the Z basis is convenient for us. And then we say that this matrix HL is many-body localized if this diagonalizing unitary has a certain locality preserving property, which is characterized by a rate alpha. Now, this locality preserving property means the following, that if you have an operator that is supported on some interval I on the chain, then there is a sequence such that, well, perhaps let me look at this then, that if you transform this operator with this unitary U, then the result can be expanded in the sequence of ONs, which have support further and further away from the interval I, but if they have support, let's say n, distance n out of the interval I, then they should be damped by alpha to the n, right? So this alpha is a decay rate, how basically how much this unitary can spread things out. Okay, so unitaries that satisfy such a locality preserving property, they are very special. Of course, the most natural way to make such a unitary is to take some local Hamiltonian and to take the time 1 evolution generated by that. Then you would get something that spreads things out, but only a bit, right? With tails that are exponentially decaying. So a system is MBL if the unitary U that diagonalizes the Hamiltonian has this locality preserving property. Okay, this is an extremely strong property. Let's quickly flash some of its consequences. So the operator DL was diagonal by construction, right? And it's also a sum of quasi-local terms. Why is the sum of quasi-local terms? Well, I just put the U and the U dagger on the other side. HL is a sum of local terms. And then I use this locality preserving property for each of the terms of HL. And then I conclude that DL is a sum of diagonal terms, but it's also, sorry, I already said it's diagonal and it's a sum of quasi-local terms. Because the diagonality here is in a basis, which is a product basis, namely the Z basis, being diagonal and being a sum of quasi-local terms means that you are a sum of diagonal quasi-local terms. That's a small exercise that you can do for yourself. So DL is a sum of diagonal quasi-local terms. In particular, P is a sum of commuting quasi-local terms. Now, since HL is unitarily conjugate to DL, HL is also a sum of commuting quasi-local terms. And if you have a Hamiltonian, which is a sum of commuting quasi-local terms, it's, I think, very intuitive that such a Hamiltonian cannot lead to a lot of transport, right? I mean, yeah, I think that's more or less clear. So if you would do the exercise that I was doing a few slides ago, or here, if you would do this exercise of defining the maximal non-equilibrium stationary current with the information that HL is a sum of quasi-local diagonal terms, quasi-local commuting terms, then you would get that this current cannot be bigger than something that is exponentially small in the length L. And the rate of this exponential decay is precisely this alpha that featured in the locality preserving property. Okay, so this is my definition of MBL. As already said, this definition, if you heard some other talks about many-body localization, it's basically what I am telling you, except that here I'm assuming some uniformity, right? So for example, in this locality preserving property, the decay that you got for this sequence ON was independent of where the interval I is located. In a disordered system, this would be quite unrealistic. So if we are discussing many-body localization as it is usually meant in the literature, then you would have to weaken a little bit this locality preserving property, allow for some bad regions where the decay can be a bit worse, and so on and so on. I think most of you are familiar with these kind of things from Anderson localization, right? But again, for my talk, I stick really to this property. It's this property that I will need. Okay, good. So here is a theorem on many-body localization in the previous sense. It's I call it many-body localization for short chains, and it says the following: with probability which is not smaller than something that decays exponentially in L. So I have a probability that decays in the system size with a prefactor that is small, because gamma is small. So with this small probability, HL is MBL. And I give here an expression for the rate. The C and C prime are constant that, of course, do not depend on the length L or on the perturbation parameter gamma. So again, we prove here something which holds with vanishing probability, right? So about a launch system, we make a claim about the system, but the claim is only valid with very small probability. So if you are interested in the original chain, then this claim is probably not so spectacular or interesting. It is useful for us when we use it for sub-intervals of this chain. You see, the point is that even though this claim, this MBL property has very small probability, if you investigate it in subchains of the chain of length L, and the subchains are of this length, logarithm L times a large prefactor, for intervals of this size, it actually becomes very likely that there is at least one subinterval where the theorem applies, where the event that this is MBL does occur. Okay, so I will on the next slide say why that implies the bound on subdiffusion. For now, I just want to say that the first time we contemplated doing this result many years ago, we thought this would be easy because you are allowing yourself to condition on an unlikely realization of disorder, right? So the result only has to hold with small probability. However, this proof turned out to be very difficult, at least for me, and yeah, I still find it very difficult. Okay, so now it's also important to say that a stronger property where, I mean, it's not, I do not have enough set up in my slides to really compare the results, but basically the stronger property here is that the MBL holds not with vanishing probability, but with overwhelming probability. But then MBL has to be defined in a less naive way. So the stronger property was first proven by John Imbrie in 2016. And our work is actually an attempt to reproduce his result and to simplify that proofs. The main ideas of his... Yes?
I thought Imbrie needed a sort of difficult, unproven assumption to prove his stuff. Is that still the case?
Yeah, well, yeah, that's true. He has an assumption on the spectrum. Since we prove a weaker result, we don't need that assumption on the spectrum, but nor does he. So, I mean, what I prove in, or what we prove in this paper, you could also, I mean, if you look at the part of Imbrie's paper where that would be proven, it would also not need the unproven spectral assumption.
I see. Okay.
So the main ideas of John Imbrie's paper are taken over, but the implementation is very different. Okay. Good. So here, I just want to make the connection between the two theorems that I stated, namely that the result on MBL for finite chains implies the result on subdiffusion. This was pointed out 10 years ago, and this argument is by now it's very standard. And I actually already hinted at that. So the main point to realize is that this current, the maximal current that was defined next to part 1, could be basically probed anywhere in the system, right? And what we do is we find the longest subinterval in the system that satisfies MBL. As I already said on the previous slide, that will be a subinterval with length basically logarithm of the total system size, right? And then we study the current inside that system, and we use the very strong insulating property of the MBL material. So this current would then be exponential in the size of that subinterval. And that subinterval is of order log L, but the constants here work in your favor so that in the end you get a polynomial bound, or rather a rational bound on the maximal current with a power that is arbitrarily large. Well, arbitrarily small, right? The power is arbitrarily negative, which indeed proves our result. So as I said, this argument is fairly standard, and I wrote it here, I described it here in a rather non-rigorous way, but there is no problem in making that rigorous, right? It just means that you have a region which is very insulating, and you use that region to say that transport throughout the whole chain must be slow, is basically dominating by that insulating region. Okay, good. So the rest of the talk is devoted to some sort of idea of the proof. Okay. So unfortunately I said that our implementation is very different from that of John Imbrie, but I'm sure I will not get, and I even did not prepare any point where you would see that difference, right? So because the first things that you can tell are exactly the same. Okay, so the proof idea is to do some successive diagonalization scheme. You start with the Hamiltonian, which you rename as H0, and then you do unitary transformations with unitaries that are locality preserving until eventually you have eliminated all non-diagonal terms. And for us, that will work with a probability with exponentially small in the size. Okay, so at each scale, so this 0, 1, and so on, which will be indicated by the letter K, that's the scale. At each scale, you write the Hamiltonian as a diagonal part, diagonal in Z basis, plus a perturbation. Okay, and then how does it go? So the Hamiltonian at scale k plus 1 is obtained from the Hamiltonian at scale k by performing a similarity transformation or a unitary transformation with some anti-self-adjoint generator, which is called A at scale k plus 1. Okay, so we take this similarity transform and we expand it. We expand it, A will be small, so you can expand in powers of A. So then you first have the zeroth order, which is this dk and the vk here. Then you have first order, which is this term and that term. And then you have higher orders in the operator A, which will be basically non-important. And the idea is always that you choose this similarity transformation so that this thing here becomes 0, right? So that the leading perturbation is cancelled by this term, so that the term that is now the leading perturbation is this next term. So that's why I label it V at scale k plus 1, right? So of course the dots have been disregarded on the next line. Okay, and extremely rough and also naive idea is that if V at scale k is of order epsilon, and this is very vague what it means to order epsilon because these are operators with a lot of structure, but let's for the moment just go with it. If that is true, then you might hope that the A, which is basically defined out of V by inverting this operator D here, that this A is also of order epsilon, and if that is the case, then this V at scale k plus 1, which is a commutator of Vk and Ak plus 1, would be of order epsilon squared. So you see that you have reduced the size of the perturbation from epsilon to epsilon square. And then the idea is that you do that infinitely often, but similar as in the KM theorem, and you eliminate the perturbation completely, remaining with a diagonal operator. Right, the diagonal operator gets renormalized along the way because some parts of the dot dot dot, or even some parts of what is sitting here, will be diagonal and have to be absorbed in the D. I will not speak about that at all. Okay, so I want the thing that I want to show you is why this is a little bit difficult, why this is subtle, and for that, unfortunately, I need to introduce a little bit of setup. So here on the next slide, there is a little bit of setup. I have to package this perturbation V as a sum of local terms, but actually it will be a sum of much more stuff, which we call diagrams, and which take value in some horrible set, which is introduced inductively. But we don't really need to worry about that. So V is written as a sum over diagrams. I have also dropped the scale here, otherwise it would get too crowded. And what you need to know about these diagrams is that each diagram has a size, right? And that's this absolute value of Vg. And then it also has an operator content, and this operator content is a local rank 1 operator on an interval I. So I is an interval on the chain, and on this interval, your Vg is basically transforming you from a spin configuration sigma 1 into a spin configuration sigma 2. On the rest of the chain, the operator just acts as identity. Okay, so it's a bit silly, but just to be sure that we are on the same page, let's try to make that a bit more explicit on scale k equals 0. So then on scale k equals 0, this interval I is just a single side. The perturbation was just x. And what we basically do, we just split this x. X is an operator that flips the spin. We split it into spin raising and spin lowering. So one diagram would be choice of a side and choice of whether you want to raise the spin or lower the spin at that side. And then, of course, the size of the diagram is just gamma. Good. So and I will notationally indicate these diagrams just by drawing small intervals centered at the side, and later these intervals will take more space. Okay, so these are intervals at scale 0, and then of course we need to look at higher scales. Okay, so here is just written the same thing again. So Vg with Vg having a size and an operator content which is locally rank 1. And then the operator A will be expanded very much in the same way. And A of a diagram G is defined by solving this equation, right? So recall that this should remind you of that equation, which was written here for extensive operators. And I am going to satisfy this equation by V is a sum of local terms. And now I will define A also as a sum of local terms, such that each local term, or rather each term corresponding to a diagram G, solves this equation corresponding to the term here with diagram G. Okay. Now, you can do that. You can solve this equation, but of course it involves inverting the operator D, or rather inverting the super operator, which is commutator with D. And so, because I chose these diagrams to be rank 1 locally, this is almost, so I'm cheating you here, but I think it's justified to cheat a little bit. So basically you are this inversion of D here brings in the energy associated to configuration 1 and the energy associated to configuration 2, energy as measured by the diagonal operator D. And so I wrote here it's an energy difference of this D, or a difference of expectation value of this diagonal operator di in the two different configurations, sigma 1 and sigma 2. So di is, you should think of at the restriction of the operator D to the interval I. Of course, there are also contributions in D that partially sit in I and partially stick out, and they are completely neglected here in this equality. So I should have made this equality mental equality. It's already here, it's not really correct. But that does not matter. So, okay, so you see that AG is very similar to VG. It has an operator content, and it inherits the size of V, but you have to divide by a denominator, and that denominator is an energy difference. Okay, good. So let's have some graphical representation for that as well. So the diagram G1 here. So we have here a diagram G1 which sits at side 1. We have a diagram G2 which sits at side 2. And now I consider the A operator associated to the diagram G2. So that just means the V operator divided by a denominator, and that denominator is indicated here by the red arc. And if I have these two operators, then I can make now an operator at the net scale. And the operator at that net scale will again be written as a sum over diagrams, but now the diagrams are objects with more structure. So actually, I take the diagram G1 and the diagram G2 at scale 0, I put them together, and the pair of them I declare to be a new diagram. So you recall that at 0 scale, diagrams were very simple. Already at scale 1, diagrams are basically sets, or here in this simple example, just pairs of 0 scale diagrams. Okay, good. So that's how it goes. Of course, the G1 and G2 had to overlap, or at least to be adjacent, because if they would not be adjacent, then this thing here, which is the operator content of VG prime, of the new diagram G prime, that would vanish. So that's why they have to be adjacent. Okay, so this is probably already a little bit complicated, and it's actually also not entirely true. As I already said, I've already cut corners, but what you should take away from this slide is that the size of the new operator of the new diagram G prime is basically the product of sizes of the composite diagrams divided by a denominator. So this red arc is the denominator here. Okay, and the support, the interval I of these new diagrams is just the union of supports of the old diagrams. So I think that's sort of intuitive. Okay, and now I am going to try to argue that this problem is a little bit difficult and you cannot do it in a purely iterative way. So I have put here again two formulas that I had on the previous slides. The formula for the support of the diagram G prime, there is here one prime too much, and the size of the diagram G prime. So as regards to that support, to that interval I, well, at scale 0, the support was one side. Now at scale 1, you basically put together two scale 0 diagrams. So that can be one side plus one side. That's two sides. And if you iterate that, you see that the typical support, or the maximal support, let's say, of a diagram at scale k is just 2 to the power k. Okay, so that's good to keep in mind. Now, for this size of the diagram, let's think what we really need, because in the very rough idea, I said that, oh, this goes to 0, but actually, actually, I need even something more than it just going to 0. I need that, well, it's not even written on this slide, but I need that there is a running coupling constant, beta k, right, such that the size of the diagram G can be written as beta k to the power size of that, or support of that diagram. You see, I wrote here that this running coupling constant should not exceed 1. Of course, it should not exceed 1, because then this size of the diagram is not even decaying with the support of the diagram. But actually, I need much more than just not exceeding 1. I need it to remain bounded firmly below 1. Right? So that at each scale, the terms that I generate have exponential decay in their support. You could ask, well, why would you need such a property? But it's rather, I mean, it would need a separate discussion. But if you start generating terms that are not decaying exponentially in the size of the support, then there is no chance of the scheme working. So all to say that I need this size of the diagram to decay exponentially with its size. And I encode that by looking for a running coupling constant beta k. Okay, so now let's look at the formula that we actually have. So the product of sizes of the diagram divided by a denominator. Now, what about this denominator, right? So this is, as I already said, this denominator is an energy difference of an operator, a many-body operator that is supported in the interval I. The interval I would be, let's say, the interval of diagram G2. Okay. So, of course, this operator D in the interval I has its Hilbert space dimension, its number of levels is 2 to the power length of this support I. So the energy differences cannot be bigger than 2 to the power minus this. But, well, basically, they cannot be bigger than 1 over the Hilbert space dimension, which is 2 to the power minus support of the interval I, right? Of course, you could say that this is the worst case. It's true that it's the worst case. It happens for a pair of configurations that in energy are adjacent. But these are there, and you cannot choose to ignore these adjacent levels. So this is, you really have to deal with these adjacent levels, and their energy difference is just of this order, right? Okay, so if we plug everything in this formula, then we see that, okay, so here I plugged in B beta at scale k plus 1 up to the power, which is the size of the support of that thing, which is 2 to the power k plus 1. And here I'd have the same thing at one scale lower, but because it comes with a square, namely this times that square has the same effect as the plus 1 here. And so this here is of the same size as that. And then we are left here with this horrible thing, with this blowing up factor, which leads to the fact that this running coupling constant is just increasing if I do things the way I did. So that, of course, we cannot afford, right? So if we do this, then after a number of steps, beta k will just become bigger than 1, which is complete nonsense, because then the perturbation is growing. So this all just to say that we cannot afford this kind of iterative estimate that assume the worst case for the denominator that is here. Okay, so what to do? Okay, so I will now investigate a bit the problem that I highlighted, and I will try to do a little bit better, right, to see what is actually happening. So for that, I will I introduce here an example of a diagram at scale 2, and let's build it up step by step. G1, G2, G3, G4, which you can think of as sitting as sides 1, 2, 3, 4, are just scale 0 diagrams. Two of these diagrams have received a denominator, so they have been promoted to A operators. At scale 1, I take G1 and G2 together, and I assemble them into one scale 1 diagram, G1 prime. G3 and G4 are also taken together, and I assemble them into a diagram G2 prime. Okay. Then the diagram G2 prime also gets a denominator. It becomes an A diagram. And so this together, now the concatenation of diagram G1 prime and G2 prime is a diagram at scale 2 that is called G double prime. And the size of G double prime, well, it is, we recall, you always put the new denominator and then you put the sizes or the product of sizes of the composite diagram. So if you do that all down to scale 0, then you get that you have the size here of the scale 0 diagrams, which will just gamma, so gamma 1, 2, 3, 4, gamma to the power 4, and there are 3 denominators, so D1, D2, D3. Okay, so far so good. Yes. And now, what we actually need here is we need that this product of denominators is smaller than some power to the size of the support of the diagram, which is I, which in this case actually just 4. And that would be okay, right? Because I'm now not doing anything iterative. I'm just estimating the whole diagram from its naked constituents up to the final scale, which is here scale 2. And there I can afford some constant or even some very large constant to the power 4, because it anyhow gets multiplied by gamma to the 4. So what this means, that's not really visible well on scale 2, but I think you will believe me. If we take the worst case for each of these denominators, so here it's a little bit silly because here the worst case for D1 and D2 is just 1 over the Hilbert space dimension, just 1 over 2. And the worst case for 3 is also 1 over the Hilbert space dimension is 1 over 4. But if we multiply all these worst case, we will in the end not get something of order C to the size of the support. However, you can basically afford one worst case, right? So for example, it could be that D3 is the worst case, is 1 over 4, but then D1 and D2 have to be basically of order 1. Okay, so that is a little bit the conundrum that we are facing. We can have a few bad cases. Some of these diagrams can be bad, but most of them have to be good. Okay, and now let's see whether I scribbled here something else. So the idea that makes this feasible is that after all, if you remember, so let's look here. So by the way, when I use my cursor here, is that visible, Ian? Or...
I mean, we see the cursor. Or
yeah,
we can see the cursor.
Good. So the point is that you see this the configuration. Configuration that was on this diagram G1 and the configuration that was on the diagram G2, they of course influence the configuration, the configuration 1, both the configuration, the initial and the final configuration, they influence the configuration of this diagram, right? So that configuration is the one that goes into defining this denominator 3. So it makes sense that if you had the worst case for the pair of configurations of diagram G1 and the worst case for the pair of configuration of diagram G2, then it's unlikely that composite configuration is also the worst for diagram D3. And that is actually what will have to be used. Okay? And so let's now try to just write a few more equations. So that we already saw. Yes. So what we will need is, and now the disorder will become necessary. Up to now, the disorder did not play any role because the problems that I highlighted up to now would not be avoided by taking a good realization of disorder, right? I mean, I allow myself to use a good realization of disorder because I want only a result which is true with low probability, but for the previous consideration, it would not have helped at all. Now I will use the disorder a bit. So what I want is that this product of denominators is actually bigger than this constant to the power 4. Now recall that this product of denominators depended on the spin configuration, on the operator content of these diagrams. In this region of size 4, I have at least 2 to the 4, or rather it's actually, I have a pair of configurations, so let's say 2 to the 4 to the square number of possible diagrams. So actually this 4 should even be an 8 here. Okay, so I should, if I have for each of these configurations this probability, I have the probability that this is bigger than my c to the 4. If that probability is down by this number, then I can sum this probability over all configurations in that region and obtain the result that this bad event is unlikely to occur for any configuration locally. But so I need to prove such an estimate, right? I need to prove this estimate, an estimate of this type. And the reason that it is possible to prove such an estimate is that for the kind of diagrams that I have been considering, these denominators can essentially be treated as independent. I mean, they are far from independent, but the estimates will be as good as if they were independent. And if they were independent, then I think I have to make the screen a little bit bigger, then you can get a bound on this probability. Why can you get a bound on this probability? As you see, I'm not very good with this tablet. Well, the probability that this product of denominators is bigger than something, you, via a Markov inequality, you convert that to an expectation of the product. You put in some fractional power s. Sorry, you put in some fractional power s because, of course, the expectation of 1 over such a denominator cannot be finite, right? Because for the same reason why such things are not finite in Anderson localization, but there is no problem in using here this fractional moment. And then if the denominators would really be independent, well, then you can factorize this and you get this. And now each of these expectations will basically be bounded by something of order 1. And so you will get here something, basically some constant to the power number of denominators, which here is 3, but the 3 is basically of the same order as the 4, and so that will be actually good enough. Now, so this is the way that the problem is actually solved. However, this way of doing things creates huge problems once I consider more complicated diagrams. So to explain that, and that's really the last thing that I will say, I want to give you a feeling a little bit for why it was possible to pretend that these 3 denominators were basically independent. Well, it was possible because I had disorders on each side. right? Here are the disorders on each side, disorders H1, H2, H3, H4. And what is basically done is that you use disorder H2 to estimate this denominator, you use disorder H4 to estimate this denominator, and then the disorder H3 was not yet used, you use it to estimate this denominator. But that, of course, requires this diagram to be sufficiently, as we call it, non-crowded. So if you consider a diagram as here, where all these denominators overlap much more, then it's impossible to assign every denominator its private disorder variable. And so such a scheme, such a thing will not work anymore, and then you have to do something else. But then also for such, as we call them, crowded diagrams, the original problem will be that the iterative estimate does not work. That problem will then be a little bit better, and so one has to consider all these intermediate cases, and that's what makes the scheme difficult. So sorry that I'm not going more in detail about that, but I think that would anyhow be hopeless. So yes, so thanks a lot, and sorry that these last slides are so horrible for people who were not there at the introduction. My overleaf broke down, so that's my excuse. But I hope it was a little bit understandable nevertheless. So thanks a lot.
Thank you very much, Wojciech, for this lovely talk. We have plenty of time for questions. So if you have any questions, please feel free to unmute yourself, or you can write them in the chat as well if you prefer to do that.
Mm-hmm. Mm-hmm.
I have a maybe dumb question. If no one else has one, of course. Maybe John can go first, sorry.
Thanks, Wojciech. That was a nice presentation and really nice piece of work. Of course, I'm interested in some of the technical aspects that you got into at the end, but I'm just curious as to whether you had something, like, it sounds like something similar to the long and the short diagrams, and but you have a different way of approaching that distinction.
We have a better name. Instead of long and short diagrams, we speak about crowded and non-crowded diagrams.
Yeah.
I think you must confess that is a huge improvement.
Yeah.
And then there are, of course, differences, but basically it's the same idea as yours. Yes, for this distinction.
But somehow, is it fair to say that because you had a slightly less ambitious, you're willing to prove something with a small probability? You just need a very small probability for it being true in order to get your result. Does that enable some considerable simplification on this aspect of crowded/uncrowded diagrams?
So you see, we did not try to do the full thing, right? So perhaps some of the things that we did would not be possible for the full problem, right? Where you want to do it with basically with probability 1. But that's not obvious to me. So what do I mean it's not obvious to me? So yes. A little bit hard to say. So I think the honest answer, which is also a little bit vague, is no. I don't see that the fact that you see, so basically, you know what we are doing, right? We are omitting resonances, right? We are not treating the real resonances. But I don't see that a lot of the simplifications that we made are actually connected to that, right? So to say it in another way, we basically needed all of your paper to do what we did, right? It's not that some sections can be omitted, right? So for example, the determinant bound, the factorials, we needed all that. So there is nothing obvious that gets simplified because we neglected resonances. It's a
Okay.
vague answer. I'm sorry. Yeah.
Yeah, but I will just more generally, I just want to say how much I appreciate the fact that you got a result without this level spacing assumption, which was always a sticking point, especially for the doubters who were looking at the numerics and not seeing these effects, and so that is a major improvement.
We'll have time for more questions if
How would it be for classical chains?
Classical chains, I think so. Nothing of our proof goes through. And personally, I don't believe the result for classical chains. So, of course, there are localization effects in classical chains, right? I mean, you have worked on that, right? Beyond doubt, there are localization effects. But I am I'm not confident, but I'm willing to bet that the result that we prove here is not true. So that if you have some classical chain, let's say some coupled rotors with some generic interaction, and the rotors would be very disordered, it's not the result that we exhibit here about subdiffusion. I don't expect it to be true. Is that an answer? And certainly none of our proof technique would go through.
All right.
And there's also a question in the chat from Pierre Wang, who asks, what would happen with another geometry or dimension?
So it's basically the same answer, except that here I think the question of whether the question of whether you can, how to say it, let's say as follows. So the having MBL on small squares, right, which would be the analog of our MBL on finite chains. I don't know whether that's feasible, but certainly our proof uses the one-dimensionality strongly, right? So I would not have no idea how to generalize that. Then also the step towards subdiffusion does not work because the argument here was very one-dimensional. Right? It sort of uses that when you have a bad region, a very localized region, it acts as a bottleneck. Two-dimension, I don't think you can make that work. And then finally, but perhaps the question, well, I don't know whether the question is about that, but most people also don't even believe in many-body localization in higher dimension anymore. So that would be a too ambitious goal.
All right. Are there any more questions?
Yes. So this is a little bit related question. So you didn't tell us how to connect this on MBL behavior to this the final conclusion about the current. Is there anything non-trivial there, or it's you sounded like it's an easy part? But...
Yeah. So, I mean, I gave this physics explanation, right? That when you have a part of your system which is very well insulating, you could say, just think of electrical circuits that has a very high resistance, right? Then the resistance of the total chain cannot be smaller than one of the resistors that are coupled in series, right?
Yeah, that sounds,
basically, yes. And so this physics argument is basically also the mathematics argument. Of course, there you don't use the notion of resistance because that's a very complicated notion, but essentially it's just the same argument. That's really easy. Yes. That's why I did not spend time on that. Yes.
Thank you. So in the introduction, you mentioned about some numerical results recently, and which raised doubt to the belief of people. But did you say anything? Is your new result related to this that in some sense?
So I mean, I should say, my references were extremely incomplete, right? There were many papers, numerical papers, that were finding that perhaps this MBL phase does not exist.
Okay.
Now, some of them, in particular, the first one, the one from the Ljubljana group, historically, I think that was the first paper that said, well, look, perhaps this MBL stuff is just not true. That paper was also claiming that there should just be finite conductivity, a finite diffusion constant. So that numerical paper we contradict. Then some other papers, they are more specifically targeting the MBL. Right. So these, for example, the reason I would say that's to me is the easiest to understand, the most direct. The work from 22 from Dries cells is not contradicting that the diffusion constant is 0, but is directly saying that it's inconceivable with all what we know that in the finite chain, well, he's basically just doing some flow analysis, right? He's considering a system in size 10, size 12, size 14, and just analyzing the data in a way that is probably a little bit better than what people were doing 5 or 7 years before that. And he's saying, well, this system seems to flow towards a thermalizing system. So we cannot contradict that, right?
Okay, thanks.
Thank you very much. Unless there are any further urgent questions. Well, thank you so much, Wojciech, for this lovely talk. This was the last talk for this calendar year. We'll meet again next year on January 14th with a talk by Wendel and Werner. I hope to see most of you there.
Bye-bye.